is most commonly used in India is the one by C.P. Kodandaraman and Subramanian. So that's the book followed mostly throughout India, and I suggest you also to follow that book. And I will be following that book. The edition that I have with me is the 9th edition. So it's important that you also have the latest edition, because as I discussed in the class, I will be mentioning which equation is available in which textbook. Sometimes I will be asking to refer to a particular page where you will be required to access the properties, access the equations or the correlations, and so on and so forth. Sometimes you will have to read from the graphs. So I will be referring to certain page, and if we all use the same edition, then the page number that I refer to will be same as the page number you are supposed to refer. So that is how it will work. If you use an older version of this book, then most likely the page numbers will be different, and then you will have to search. So to avoid all that confusion, it is better to have the latest book. So as I am using my personal copy is the 9th edition, so I suggest you also use the same book. So in this class, we will actually uh, go through for the first time, go through this particular data book and see what is available in the data book. As a part of today's lesson, that will also be there. So in the last class, what we have seen is the derivation of the heat conduction equation in a three-dimensional transient situation in a case where there is heat generation. So I'll just share my slides here. So this is the heat conduction equation that we have seen in the last class. This is derived in Cartesian coordinates. So Cartesian coordinates are easy to follow for all of us. So that's the that's the coordinate system chosen. The advantage of Cartesian system is that the areas, you see here, the area on the left side will be same as the area on the right side. So with this advantage, it will be a little bit easier to follow. So that's the only thing. When you come across the cylindrical coordinates and spherical coordinates, as the radius changes, the area also will change, which will bring about its own disadvantages. I mean, its own complications. I wouldn't say disadvantages, but its own complications. So because of that, we use this Cartesian coordinates to introduce. So the same way, when we derived the continuity equation in fluid mechanics, we first started with the Cartesian coordinates because it is easy to follow, easy to understand, and easy to visualize also. So this is the element, the cuboidal element that has been chosen in a solid, and we have evaluated the energy balance. In this case, the energy balance means the heat balance. So all the heat going in has been accounted in all the three directions. All the heat leaving in the three directions is accounted for, and when you subtract the heat leaving from the element from the heat entering the element, you will get the net amount of heat entering the element. So that is one term, that is the net heat entering. And sometimes we will have situations where there is a heat generation also. So that heat generation has been accounted. And when the amount of heat entering and heat generation is not same as the amount of heat leaving, then there will be some energy storage. Either the body will get hotter or the body will get colder. So this is called as energy storage. When the body gets hotter, the energy storage quantity will be positive, otherwise it will be negative. So using this, we have we have framed some equations. We have used the fundamental equation that we have used is this one. This is the Fourier's law of heat conduction in the x direction, and we have evaluated what is the amount of heat conducted on the left face in the x direction, and evaluated what will be the amount of heat leaving on the y direction, and when we subtract, we will have a term left. So that things we have taken care of, and we have used this general energy balance equation. Energy in minus energy out, that gives the net heat energy entering, and then E dot G is the energy generated, and E dot ST stands for storage or accumulation. So this is the energy stored. Remember in this subject of heat transfer, when we talk about energy, we mean heat energy. So using this, we have derived this heat conduction equation in Cartesian coordinates. There are three terms on the left hand side having the partial differentials. So the partial derivative is because the temperature is the dependent variable, and x direction, y direction, and z direction, these are the space coordinates, and the temperature is dependent on x, y, and z directions. Therefore the temperature is a function of more than one variable, and other variable also is there. This is the time. So temperature is a function of space as well as time, three space coordinates, and time is generally, sometimes we call it as the fourth dimension. So basically here in this case, if we use that language, we can say that the temperature is a function of four dimensions. Therefore we have this partial differential equations. Now, if you see this partial differential equation, you will see that when you take out k from here, you will see that it will be k multiplied by dou square t by dou x square. That means the dependent variable has a power of 2. So this becomes a second order partial differential equation. Then there is this heat generation term. Can you tell what is the unit of this heat generation term? Q dot. We have seen in the last class. Heat generation is usually mentioned as a volumetric heat generation.
Watt per meter cube.
Yes, exactly. So volumetric heat generation is considered in most heat transfer problems, and the unit is watt per cubic meter. Okay. So the three terms on the left hand side indicate uh, the heat conduction in each direction. Net heat conducted in the x direction, in the y direction, in the z direction, heat generated, and heat accumulated. So all these things are considered. So this is the most general form of the heat conduction equation. Very rarely we will have all these terms. So in many practical applications, this can be simplified. For example, the most common simplification can be when the thermal conductivity is anisotropic. Anisotropic means not dependent on the direction. That means no matter what direction, the thermal conductivity remains the same. So in such a case, we say that the conductivity is constant, thermal conductivity is constant. So in which case we can bring out this thermal conductivity out of this partial differential, and we can take it to the other side. So when we take this conductivity out, you can multiply this dou square t by dou x square here, dou square t by dou y square here, dou square t by dou z square here. And then when we divide the entire equation with k, you will have q dot by k. So that comes here, and rho Cp by k, it comes here. But rho Cp by k is another important property in heat transfer, that is called as the thermal diffusivity. So this thermal diffusivity is a quantity which indicates how quickly the heat diffuses throughout the mass. So it sometimes is related to the transient heat conduction. So this parameter actually comes in transient heat conduction. So we shall see that in that module number 2. So we'll see, I will explain this thermal diffusivity later. Then another special case is when the conductivity is not constant, but there is no transient conditions. So in such a case, we have the steady state condition, and therefore the right hand side of this term will become 0. So dou t by dou tau becomes 0, then we will have this equation. And one more simplification is 1D, when the heat transfer is one directional in nature. So we force the heat transfer in a particular direction. That means we block the heat transfer in the other directions. For example, you must have done, or you must have seen this experiment on heat conduction in a metal rod. So that's an experiment where we measure the thermal conductivity of a metal using a metal rod, where we force the heat to travel in the longitudinal direction only by insulating the radial face. So there we are forcing the heat transfer to take place in one dimensional conditions, and in such a case we won't have this term and we won't have this term. If there is no heat generation, we won't have this. and if there is no transient term, we won't have this. Therefore, the equation will be dou by dou x multiplied by k dou t by dou x. Okay, but now here the temperature is only a function of one parameter x, the space coordinate. Therefore, this equation can be written as d by dx of k dt by dx is equal to 0. So that means the partial derivative symbol dou is now replaced with the ordinary differential d. And if k is constant here, then this equation will become d square t by dx square. K can be brought out here. This will be equal to 0. But then since k is a constant and it is a non-zero term, k can be taken to the right hand side, and this entire equation will become d square t by dx square is equal to 0. So in this way, things can be simplified. Okay. Now in the last class again we have also seen okay, that's the problem with me. All right. We have also seen that under certain circumstances, the equation takes different forms and some names are given to those equations, especially after the scientists who worked extensively in this field of heat transfer. So you can see the first equation that you see here is the most general form of equation. The first one is the most general form considering everything. Then you see that if k is constant, then we can bring the k out of the partial differentials, and then with this the equation will take this form, and this form is called as the Fourier-Biot equation. And then if there is no transient term, if this dou t by dou tau is equal to 0, then the Fourier-Biot equation will take this form and it is called as the Poisson equation. So Poisson equation is something that considers heat transfer in the three directions and also the heat generation term. And if the generation is absent but the transient term is present, that means dou t by dou tau is non-zero, then we have what is called as the diffusion equation. So this is not really named after any scientist. It's a diffusion equation because it is quantifying the diffusion in the directions in space and also in time. And finally, we have this Laplace equation where only the space is playing a role in determining the temperature, the time is not playing any role, and also the heat generation is absent. So the Laplace equation is the most simplest of all equations in the three dimensions. So dou square t by dou x square, dou square t by dou y square, dou square t by dou z square is equal to 0, which does not have the transient term and which does not have the generation term. That is called as the Laplace equation. And in this Laplace equation, if the y direction is not influencing the temperature, or the temperature is independent of y direction and the z direction, then only one term will be left, dou square t by dou x square. Only that term will be left. That will be the simplest form of the Laplace equation. Similarly, like we have done for the Cartesian coordinates, we can do the same for the cylindrical coordinates. So you can see here in a cylinder, you see this is a cylindrical geometry. In this cylindrical geometry, a cylindrical element has been chosen and it has been magnified here, and this cylindrical element has got a radius dr. Now all the dimensions are represented differentially because these are the infinitesimally small dimensions. So differential radius dr, differential height dz, and for cylinders the third dimension is the tangential direction, which is phi direction. So you can see here r theta and phi, r phi and z. R is the radial direction, phi is the tangential direction, and z is the longitudinal direction. So these are the three principal directions in the cylindrical coordinates. And if you do the same exercise that we have done for the Cartesian coordinates, that means write the Fourier law of heat conduction at the entry side. For example, let us see this. This is the heat entering in the R direction, and this is the heat leaving in the R direction. So if you quantify both of these, that means for QR, if you write the Fourier equation, and then for QR plus DR, you differentiate that Fourier equation accordingly using the Taylor series expansion, then you will have these terms. So again, applying the energy balance equation, E in minus E out plus heat generation is equal to the heat stored, you will end up with this equation of heat conduction for cylindrical coordinates. So this is the equation for cylindrical coordinates. Okay, so this is the heat transferred or heat conducted in the radial direction. So this term, this is the heat conducted in the tangential direction. This is the heat conducted in the longitudinal direction, heat generation, and heat stored. So you can see there are three terms for each of the dimension, and then there is a generation term, there is a storage term, exactly like in the Cartesian coordinates, but the geometry parameters are different compared to the Cartesian coordinates, so those things will be different here. Likewise, for spherical coordinates, you can see here there is a spherical geometry. In spherical geometry, there is a spherical element stored.
Could you please show the last slide again?
Sorry?
Could you please show the last slide again?
Okay. What is it in the last slide?
No, so I was just confirming whether it was written right.
Yeah. Now, in the spherical coordinates, in a spherical object, you can take an element which represents the spherical element, and the dimensions of the spherical element will be r, the radial direction, phi, the tangential direction, and theta, r, phi, theta. Theta is what is called as the azimuthal direction. I'll write it down here. Have you heard of this word azimuthal before?
Yes, sir. There is something called azimuthal constant.
Azimuthal constant. If you have done this course on renewable energy, have you done this course? Was it offered to you? Because I don't remember actually students taking this course. Anybody has taken this course? Renewable energy. You will see that there is one of the renewable energies is solar energy, and the solar inclinations. To describe the solar inclination, one of the term used is the azimuthal angle. Therefore, in spherical coordinates, we have this azimuth direction also. So r is the radial direction, phi is the tangential direction, this one, and theta is the azimuthal direction. So if you rewrite the energy balance equation with the Fourier law of heat conduction and expand it and simplify later on, you will have this. You can see this now. This is the heat conducted in the radial direction, heat conducted in the tangential direction, heat conducted in the azimuthal direction, heat generated, and the heat stored. So this is how you have these three equations. So in the next slide, I have summarized all these three terms. Okay, so you can see all these three equations in one place, the most general form of all the three equations. That means three-dimension transient with heat generation and with the thermal conductivity depending on the direction. So this is the most general equation possible, or we can also say that this is the most complicated equations possible as far as the heat conduction is concerned. So corresponding to the first term in the Cartesian coordinates, we have one term in the cylindrical coordinate and the spherical coordinate. Similarly, for Cartesian coordinate, the second term, we have the second term here. And the third term, the heat transfer in the z direction Cartesian coordinates, z direction in the cylindrical coordinates, and azimuthal direction in the spherical coordinates. Then we have the heat generation in all this, which is volumetric heat generation, and also the heat storage. Okay, so you can see that even though the equations are having different terms because of the difference in the geometry, the physical meaning is still the same. Okay, but obviously solving a equation in Cartesian coordinates looks simpler compared to the equations in cylindrical coordinates, and the spherical coordinate equation seem to be the most difficult one. Okay, we rarely go for spherical coordinates. Even if we go for spherical coordinates, we will limit ourselves to one dimension. So don't worry much about the solution aspects, some of which we will see in today's classes. Now, we have seen the equations, the three heat conduction equations in the three geometries. Why do we take this Cartesian, cylindrical and spherical geometry is these are the standard geometries for which mathematical treatment is possible. So we have equations for a cuboid, equations for a cylinder, equations for a sphere, and we can easily write the governing equations for these three standard shapes. If we take any random shape, mathematically it becomes extremely difficult. Therefore, even if you have noticed in fluid mechanics, we derived the continuity equation in Cartesian coordinates, cylindrical and spherical coordinates only, because these are the standard shapes. When the shape is not standard, like in most practical applications, then what to do? That's where the softwares will come into picture. Software packages will come into picture, like finite volume method, finite element method, and so on, which we shall see later on. Okay. But as of now, let us stick to these three standard shapes and how to solve this. Now we know that these are differential equations. These are not ordinary differential equations. These are the partial differential equations. That means that the dependent variable, which is the temperature in this case, is dependent on the three space coordinates, one time coordinate, and also it is having variable thermal conductivity. That means to solve this equation, we will need to know the relation between the thermal conductivity and X to find what is the relation between the temperature and X, Y, Z, and tau. So these are all the issues involved. So the heat conduction equation is a partial differential equation with temperature varying in space, X, Y, Z direction, and in time. So I just simply mentioned X, Y, Z directions because this represents the Cartesian coordinates. If you want to mention in cylindrical coordinates, you should say R theta Z, and in spherical coordinates R phi theta. Okay. Now, since it is a differential equation, differential equations can be solved with the boundary conditions available. Now just see how many unknowns are there in this equation. How many unknowns are there? Temperature is the unknown, but to solve this, you see this is a if you take k out, it will become dou square t by dou x square. That means you will have to differentiate. See, this is a differential equation. To solve the differential equation, you will have to integrate it. When you integrate, every time you get one constant of integration. Now, since here we have dou square t by dou x square, that means you will have to integrate twice because this is a second order equation. When you integrate twice, you will get two constants of integration. So you will need two conditions so that you can evaluate these two constants of integration. That means you need what are called as the boundary conditions. Similarly, you see this dou t by dou tau. To solve for this temperature with respect to time, you will have to integrate this once, which means that you will get one constant with respect to time. That is called as the initial condition in calculus. So you will need one initial condition to take care of this term, and you will need two boundary conditions to take care of this term. And not just two boundary conditions. See, each term dou square t by dou x square, this needs two boundary conditions, one in the x direction, left side of x direction, one in the right side of x direction. Similarly, dou square t by dou x square, you need two boundary conditions. Dou square t by dou z square, two boundary conditions. That means you need 6 boundary conditions and one initial condition to solve this problem. So boundary conditions or initial conditions are needed. Now, if you consider the simplest form of it, that means you consider only one dimension and without heat generation, then you will need two boundary conditions only. That means dou square t by dou x square only is present. So you will have two boundary conditions. You will need two boundary conditions and one initial condition. So since the equation is a second order in space, two boundary conditions are needed. Two boundary conditions are needed in each direction. In x direction 2, y direction 2, z direction 2. That means 6 boundary conditions for the general case, And also, since the equation is the first order in time, that means it is simply dou t by dou tau. It's not dou square t by dou tau square. Dou t by dou tau, so it's first order, and therefore you will need only one initial condition. So with these conditions, you will be able to solve. So what happens is, with these conditions, you will have enough number of equations and enough number of unknowns. So from mathematics, we know that the number of unknowns should be same as the number of equations. The same applies for the partial differential equations also. So you need some boundary conditions and some initial conditions. What is an initial condition? Initial condition is the condition where the time is equal to 0. See, in physics, in your high school physics or in plus 2 physics, you have seen some examples of particle motion, particle dynamics. A problem statement is something like this: you drop an object having a certain mass from a cliff, and at t is equal to 0, that initially this object has got no velocity. That means you are simply dropping it and it is falling down by gravity. But there can be another case also where the initial velocity is not 0. It is you are releasing the object by giving it certain velocity. That means you are flinging it with certain force. Therefore, there is some velocity for the body. So in such a case, the initial condition will take the velocity having a certain magnitude. It can be 2 meters per second or 5 meters per second or whatever. So that is called as the initial condition. That initial condition is needed. And apart from the initial condition, to solve these problems, we need boundary conditions also. So in this particular slide, you are seeing some boundary conditions, some possible boundary conditions. The most common boundary condition, or the most simplest boundary condition, is called as the constant surface temperature boundary condition. That means in an object where you are trying to find out the temperature distribution, you know that surface temperature, you know the temperature of one surface, let us say this surface is given. That's the simplest one. Let us say this temperature is 100 degrees Celsius or 50 degrees Celsius. So this is called as the constant surface temperature condition, and in heat transfer language, it is called as the Dirichlet boundary condition. Dirichlet boundary condition after a person. So you can say mathematically this is represented as temperature. See, temperature at 0 and t. T is time. Small t is time. So that means the I will write the general form: temperature as a function of x and t is x and t. This is the general temperature is a function of space and time. Now, when x is equal to 0 and x is equal to 0, that means at this point x is equal to 0, we have temperature as a function of space. Now space is 0 and any time is equal to some value Ts, which means no matter what the time is, the temperature at that point, no matter what the time, the temperature at that point is remaining constant, the constant temperature. Now this kind of a situation arises when you are transferring heat using methods like boiling or by condensation. You know, boiling and condensation process are phase change processes where the temperature remains constant no matter how much heat you supply. So that those conditions will have this situation where the temperature is constant irrespective of the time. Time may be changing, but the temperature is constant. So that is the most simplest form of boundary condition, called as the constant surface temperature condition or Dirichlet boundary condition. The second one is a constant surface heat flux condition. You know the heat flux. Heat flux is the heat transfer per square area. So heat flux condition, heat flux is represented as a Q double prime. Okay, Qs here, Qs, S is the surface. So at the surface, the heat flux is constant. Now this kind of a heat transfer boundary condition is possible when you are supplying heat using electrical resistors. So using electrical resistors, what we do is we simply supply a certain amount of voltage and current, and the amount of heat generated is a product of the voltage and current. So that means no matter what the time is, we are continuously supplying the same amount of energy, same amount of heat energy, and also the surface area is remaining constant. So the heat is constant, the surface area is constant, therefore the heat flux is constant. So in such situations, what happens is, since the heat flux is constant, the temperature keeps rising. So the temperature inside the body keeps rising, and because of that, we have this constant surface heat flux condition. So in such a case, it is represented as constant heat flux at this point is minus K dou T by dou X at X is equal to 0. So this heat flux is given as minus K dou T by dou X at this particular point. So heat flux is 0. So this constant heat flux condition is called as a Newman condition. Okay. Now, a special case of the Newman condition is that of a insulated or adiabatic surface. We know that adiabatic means there is no heat transfer. So, in heat transfer subject, in the field of heat transfer, adiabatic condition is also called as a insulation, because insulation stops or blocks any heat transfer. So, in that case, the heat flux will be equal to 0. So, heat flux is equal to 0. That means this term dou T by dou X at X is equal to 0 is equal to 0. So, at this point, the heat flux is 0. Now you see here dou T by dou X is equal to 0. Dou T by dou X, let us say it is simply dt by dx by removing the partial derivative. Now this dt by dx is equal to 0. dt by dx, what is that? We call that as the thermal gradient. So whenever there is an adiabatic surface, the thermal gradient will be equal to 0. That means the temperature will not change with time. The slope that slope will be infinite. So you see here, the slope will be equal to 0, not infinite. Slope will be equal to 0. So how to represent this here? You see here, at this point, this curve is kind of flattening here. And on the other side also, if you try to take a mirror image on the other side, let us assume there's an object, the same kind of object like this side. And if you take the temperature profile on this side, on the left side also, it will be kind of a mirror image. So this and this are mirror images. So that is what will happen when you have an insulated surface or an adiabatic condition. So at this point, the thermal gradient will be equal to 0. So this is the third boundary condition. There is no specific name given to the third boundary condition. The final boundary condition is called as the convection surface boundary condition. So convective heat transfer, if it takes place on this surface, you see here on this side, if there is some fluid moving and it is having a temperature T infinity and having a heat transfer coefficient H, then there is the surface condition here. The heat transfer at this point, see, the heat should transfer from this medium to the surface by convection. So the convective heat transfer should be equal to the heat conducted inside. So at this heat conducted here should be equal to the heat convected on this side. So if we equate the heat convected at the surface to the heat conducted into the body at this surface, then you will get this convective surface condition. So this condition also is not given any particular name. So we have two boundary conditions called as the Dirichlet boundary condition, which is constant temperature boundary condition, Newman boundary condition, which is the constant heat flux boundary condition, and there are two more boundary conditions, one of which is the adiabatic condition and other one is the convection surface condition or the convective boundary condition. One boundary condition which is not mentioned here, but it's also important, but rarely we come across in this course, is the radiation boundary condition. That means instead of convection here, if there is radiation taking place, then you will get that boundary condition. So how do you do that is, in this equation, instead of convective heat transfer, we will use the radiative heat transfer equation. That is what is that equation? Stefan Boltzmann equation for heat transfer, that we will be using it for the radiative heat transfer. That means instead of H multiplied by T infinity minus T, we will use epsilon sigma T infinity square minus T surface square. So that kind of boundary condition can be written. Or we have seen how to linearize the radiative heat transfer. So in such a case, we can use this same condition, but in place of H, which is the convective heat transfer coefficient, we have to use HR, which is the radiative heat transfer. Okay, so I don't want to dwell much longer on this particular boundary conditions, because at this point of time probably it could be confusing to you and could be intimidating to you. So you will see that as far as conduction is concerned, especially the one-dimensional conduction is concerned, it is not as difficult as it appears. Things can be simplified. Your fundamental knowledge of calculus, the differentiation and integration that you already know, is sufficient to solve these equations, which we shall see very shortly in this class. Now, what you see in this equation, this screen, is a combined 1D conduction equation, which is easy to remember. Now, you see here, this is called, this is a general equation. This equation is a general equation, and you see here, this is written as 1 by r power n, dou by dou r of r power n k dou t by dou r plus q dot is equal to rho Cp dou t by dou tau. So, a first glance of this equation tells you that this is a one-dimensional conduction equation having heat generation and having transient conduction also. Okay, this is a general equation in one dimension only. Now, if you want to write this equation for a plane wall, all you have to do is substitute 0 in place of n, 0 in place of n, and x in place of r. So what you do is, if you do that, what you will get is 1 by r power 0 dou by dou x of r power 0 k dou t by dou x, dou t by dou x plus q dot is equal to rho Cp dou t by dou tau. Now 1 by r power 0 is 1, so this term will vanish. So this one also will vanish. So what you will have is dou by dou x of k dou t by dou x plus q dot is equal to rho Cp dou t by dou tau. So in this way, from this general equation, you can derive the equation for plane wall. Similarly, if you substitute n is equal to 1, leave r as it is, n is equal to 1, it will becomes the equation of a cylinder. Similarly, n is equal to becomes the equation of a sphere. So you can derive this 1D heat conduction equation in spherical coordinates and in cylindrical coordinates using okay, there is some problem with my so you can derive the equation in cylindrical spherical coordinates using this this simple equation and making these simple substitutions. Okay, very rarely we will go for the three-dimensional equation. Now we will move on to one-dimensional steady-state conduction. That means the dou t by dou tau term, as of now, we will not consider. We will consider that in the next module. So in this module, we'll deal only with steady-state conduction, one-dimensional steady-state conduction. So it may consider heat generation, it may not consider heat generation. So you see here, heat transfers predominantly in one direction. So if it is a Cartesian coordinate, we generally take it as x direction. In the spherical and cylindrical coordinates, we take it as the r direction. Temperature is independent of time. So dou t by dou tau is not considered. Then simple for analysis and useful in numerous engineering applications. So even though it appears to be extremely simplified, it has got its own application. For example, in fins, in slabs and in furnaces, we use this treatment. to find out the temperature distribution inside the object. Okay, so you see here, this is the one-dimensional heat conduction in Cartesian coordinates. The first term is written, the heat generation term, and the heat transient term is now 0. Okay, now this, since now the temperature is dependent only on the x, it's not dependent on y and z directions, it's not dependent on time. So this partial derivatives now will become the uh, the ordinary derivatives. Okay, so we have this dou by dou x of k dou t by dou x will be d by dx of k dt by dx, and this will be equal to 0. Now, if there is no heat generation also, then q dot will vanish, and all you have will be d by dx of k dt by dx is equal to 0. Now, since k is function of x only, we can actually take it out because we are considering only x direction, and k is function of x only. So k will remain constant, and we can actually take k out of the derivative for much simpler treatment. Okay, now we will consider the plane wall, a geometry called as a plane wall. So the plane wall is something you can very easily visualize, the wall of your house. You can imagine the situation. You have a room in your house, and one side of that room, one wall of that room is on the east side. Now we know that the sun rises on the east, and therefore that particular wall will be subject to the early solar radiation up to 12 o'clock in the morning. Then the sun shifts to the west side. So if that room also has a west side wall, then the radiation will be mostly on the west side wall. So this particular walls are subjected to constant heat radiation, constant heat flux from the solar radiation. So that is the situation. In such cases, we can use this particular plane wall example. Also, many furnace walls have uh, this plane wall situation where the inside of the wall is subjected to hot metals, and outside of the wall is subjected to atmosphere, ambient temperature. So we have this situation where we can use a plane wall for many useful applications. So how to derive the thermal distribution, the temperature distribution inside a plane wall? That is what we will see now. So the beginning of this is, we are assuming that it's a 1D steady state and a plane wall, and also the heat generation is 0. There is no heat generation. So in such a case, the differential equation will be ordinary differential equation, and it will take this form, d by dx of k dt by dx is equal to 0. This we have, you know that this is the differential equation. To solve a differential equation, we will have to integrate it. It's just like the integral equation. If there is an integral equation, to solve it, we will have to differentiate. Likewise, in this case, we will have to integrate it. So you see here, this is d by dx and it's dt by dx. So if you expand it, it will be d square t by dx square. That means it's a second order equation in temperature depending on only x. Therefore, we will have to differentiate it integrate it twice. So we will carry out the first integration. On the first integration, this d by dx will vanish, and what remains is only k dt by dx. But then there will be one on the right hand side, it is 0. Therefore, we will have one constant of integration, c. So this k dt by dx is equal to c, and if you take this k to the other side, here, since k is dependent now only on the x direction, therefore k is treated as constant. So dt by dx is c by k. This c by k is treated as another constant c1. Now you can see that this equation has reduced to dt by dx is equal to c1. Now we can integrate this once again. Dt by dx, if you integrate, it will become t. That will be equal to c1x plus c2. So if we take integrations here, dt by dx on integration will become t, and C1, when you integrate with respect to x, it will be C1x and C2. So you see T as a function of x is C1x plus C2. So what happens is we have a temperature distribution, but temperature distribution as a function of x, but we have two constants to evaluate. Now the easiest way to evaluate these two constants is by using the boundary conditions, especially the constant temperature boundary conditions. So you have in this particular slab, we have one constant wall temperature on the left hand side, which is Ts1, and another one as a Ts2. So at x is equal to 0, we see x is being measured here. So at this point x is equal to 0. So at x is equal to 0, the temperature is Ts1. Similarly, at x is equal to L on this extreme, the temperature is given as a Ts2. So if you substitute x is equal to 0, T is equal to Ts1 in this equation, you can evaluate the value of C2. C2 is equal to Ts1. Similarly, at x is equal to L, if you evaluate, T will be equal to Ts2. That if you substitute, you will get the constant value C1. So C2 is Ts1 and C1 is Ts2 minus Ts1 by L. So now we have the values of both these constants in terms of the known temperature, which are the boundary conditions. Therefore, we can substitute in this equation the values of C1 and C2, and then you will get the temperature distribution in this form. So you can see here T as a function of x is equal to Ts2 minus Ts1 whole thing multiplied by x by L. X is the distance. You see, x can take any value. It can be here, 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 here. So x changes from 0 to L. So you can give any value of x from 0 to L or in between x0 and L, and you will be knowing the temperature. So the temperature is equal to Ts2 minus Tn by Ts1 multiplied by x by L plus Ts1. So this is one equation, which is basically called as the temperature distribution. Now, sometimes in textbooks, this equation will also be written as T of x minus Ts1 by Ts2 minus Ts1 is equal to x by L. You see here, this Ts1 is taken to the left hand side, and this term in the bracket is taken to the left hand side. So this is the form you get. So in some books, you will have this equation as the conduction the temperature distribution. Okay, so this is what you will see. Now I want all of you to open your data book, page number 52, heat and mass transfer data book. Page 52. So as I said, mine is the 9th edition. Okay, so in this book, you will see in this book you will see the first equation. You can see here R is equal to L by Ka is written, and after that you can see T1 minus Tx by T1 minus T2 is equal to x by L. I hope you can find this equation. Now I cannot overemphasize the importance of having a data book in your hand. T1 minus Tx by T1 minus T2 is equal to x by L. So this is the equation that is given in your data book. So in this way, you actually do not have to memorize many things in heat transfer. You can very well access them from the data book, but for saving time and to access them quickly, you should be familiar with the data book. So as a part of this course, we will also teach you how to access all this information, equations, the property values, and so on from the data book. So with this, I would like to stop for this class. So if you have any questions, I think I can spend a couple of minutes on that to answer your questions. Any questions?
So all these conditions are the steady state conditions for defined shapes. For any shape is not defined properly, so how would the steady state condition for that be?
See, whatever may be the shape, the you're talking about the boundary condition or the steady state?
Steady state, boundary conditions and the steady state conditions both, sir.
What's the question?
So these are all the defined shapes. What if I have
These are well defined shapes, yes. See,
Yes,
even
sir.
for even for ill defined shapes, I think that's what you are trying to ask.
Yes,
Ill
sir.
defined shapes, some random shape. Okay, for that also steady conditions can prevail. The boundary conditions, like we have seen, the constant temperature boundary conditions, such conditions are also possible. So the boundary conditions that we have discussed, they are general boundary conditions, valid for any shape.
Okay, sir.
Right. All right. Let me take your attendance now. Mrutunidhi,
Present, sir.
Flash,
Present, sir.
Ancharian,
Present, sir.
Madhusudan,
Present, sir.
Pranav Dilip,
Present, sir.
Nisar, Srivatsan,
Present, sir.
Mitrayan,
Present, sir.
Trishant,
Present, sir.
Villalagan,
Present, sir.
Niranjan,
Present, sir.
Vaibhav Karan,
Present, sir.
Abhijit Menon,
Present, sir.
Praveen,
Praveen present, sir.
Adil Sinju,
Adil present, sir.
Chintan,
Present, sir.
Hamza Hassan,
Present, sir.
Ayush Tripathi,
Present, sir.
Harshavardhan,
Present, sir.
Hemant Kumar,
Yes, sir.
Present, sir.
Chandramouli Pratap Singh,
Present, sir.
Shubhwania,
Present, sir. Present, sir.
Sai Rohit,
Present, sir.
Sri Raman present, sir.
Present, sir.
Deepesh,
Present, sir.
Venkat,
Yes, sir.
Srikumaran,
Present, sir.
Sundar Krishna,
Present, sir.
Pranav,
Present, sir.
Jayanti,
Present, sir.
Niket,
Present, sir.
Adri Narayanan,
Present, sir.
Ajit,
Present, sir.
Harish Raghav,
Present, sir.
Rahul,
Present, sir.
Firoz,
Firoz present, sir.
Nihar,
Present, sir.
Vishnu Karthik,
Present, sir.
Gauri Shankar,
Present, sir.
Motishwar,
Present, sir.
Jay Prakash,
Yes, sir.
Suja, Prem Kumar,
Yes, sir.
Charan Sarvesh,
Charan present.
Charan Ajay,
Present, sir.
Reynold Simon,
Present, sir. Present, sir.
Ish,
Present, sir.
Jnanakshaya,
Present, sir.
Present, sir.
Varun,
Present, sir.
Rao,
Sir, Varun present, sir.
Ish, Krishna,
Yes, sir.
Vedant Madhur, Anand,
Present, sir.
Ni, Priya Vasan,
Present, sir.
Kalai Priyan,
Present, sir.
Narayanan,
Anish present, sir.
Santosh Raj,
Yes, sir.
Keshav Kumar,
Present, sir.
Ash Kumar,
Present, sir.
Karthik Prasanna, Sai Kaustubh,
Yes, sir.
Varun Ahalya, Varun Ahalyan,
Present, sir.
Sarvesh Krishnan,
Present, sir.
Elsie Femina,
Present, sir.
Effet Gionel,
Present, sir.
Amal.
Present, sir.
I will call the absentees quickly. Siddharth, Palanivel, Kritik Krishna, Chaturvedi, Avito,
Present, sir.
Suja,
Sir, Suja sent in chat box, sir.
Varun,
Sir, Varun said he couldn't access the mic, sir.
okay, Vedant Madhur, Shivani,
Present, sir.
Shankar Narayanan, Karthik Prasanna. All right, so I'll stop here and we'll meet again on Monday.